Welcome to the tutorial talk entitled Introduction to Electromagnetic Field Metrology, focusing on how we are chasing the trueness of the measured value. My name is Takehiro Morioka from the National Metrology Institute of Japan, which is one research area of the National Institute of Advanced Industrial Science and Technology. Before going into the tutorial, many of you might have never heard the term metrology. Here I show two definitions. One is from famous English dictionary Collins, and the other is from International Vocabulary of Metrology. Simply to say, metrology means measurement science, whatever you are measuring. My talk today contains these topics, starting with a brief overview of antennas in electromagnetic compatibility EMC measurements, not communications. A well-known parameter characterizing antennas as a sensor against the electromagnetic field in space is antenna factor in EMC, or gain in communication. Then we discuss methodologies, how to obtain antenna factors of an antenna as accurate as possible, followed by uncertainty analysis. Some of you might hear about uncertainty. To claim the reliability of the measured results, especially in the metrology field, uncertainty analysis is an avoidable way. At the end of my talk, I'm going to touch a little bit upon the international framework, realizing the equivalence of the measured results anywhere around the world. Okay, let's start with the relationship between EU field measurement and antenna characterization. Take a look around us. How many devices can you find working pure mechanically without electronics? It is getting difficult to find such a device. With a rapid density increase of electrically controlled devices, they should be located in a limited space, and interference between devices may result in a serious system fault. Accordingly, careful investigation should be carried out in viewpoint of electromagnetic compatibility before putting products into the market. Some of you may have been aware already that most of the regulations and standards, not limited to those for EMC tests, require E-field strength measurements. Electric and magnetic field strengths radiated from or impinging on the device are fundamental quantities to be measured, since they are considered to have tight relationships with interferences, such as stability and performance of a device. However, these free space parameters cannot be measured directly. Thus, an antenna is employed and transform a free field quantity to the quantities in waveguide, such as power and voltage. To measure free field parameters accurately, antenna and probe characteristics as a transducer are very important. Such characteristics including antenna gain, antenna factor, radiation and receiving patterns, and many others. In other words, accuracy of the free field measurement depends on the accuracy of the calibration of the antenna parameters. However, unfortunately, these free field parameters are not independent to the measurement environment. Conditions inside the waveguide are controllable, and you can realize the environment very close to be ideal. You can design and realize a characteristic impedance of coaxial transmission line to be 50 ohm accurately. In contrast to this, free space required in antenna measurement is one of the most difficult conditions to realize, especially at a low frequency. One more thing that you have to keep in your mind is that your antenna coupled with the surrounding environment when you use it, and the antenna characteristics may not remain the same as the calibrated one any longer. You may have a big number of antenna sections, since antennas have been developed to fit the application purpose like mobile communication and radar. So we should select a suitable antenna type for the measurement purpose. With the development of telecommunication and electronic devices, the requirements of the electromagnetic field measurements are getting difficult. To carry out a reliable measurement, the receiving antenna characteristics are pretty important. Ordinary antennas you may use in daily measurement should be the broadband antennas, such as a biconical and log-periodic dipole array antenna to cover a wide frequency range of the measurement by a single antenna. However, in viewpoint of the precision measurement, an antenna that has a simple structure is a good choice. A dipole antenna is one of the fundamental antennas, and it has many advantages due to the simple structure, such as high polarization selectivity and predictable characteristics. The dipole antenna is a balancing antenna and requires a balance-unbalance transformer in the ordinary measurements, since it is assumed to be exactly excited by the ideal balance source. One popular antenna parameter among EMC engineers is antenna factor. This parameter is not independent to some other antenna parameters such as gain and effective length, but one advantage to employ antenna factor in measurement is its simplicity. When your measurement instrument indicates the measured voltage of VR by putting your antenna having the antenna factor of F at the measurement location, the A-field strength parallel to the antenna element can be estimated by multiplying VR with F. However, to define antenna factor, some additional conditions need to be specified. Since VR changes with respect to the terminal condition, ZL should be specified. In general, it should be 50 ohm, that is a common input impedance of the measuring instrument. Regarding the A-field, it should be an ideal or quasi-plane wave. Since when a half-wave dipole antenna element is used, a slant incident plane wave introduces deviation. The illuminating E-field should be parallel to the element axis. This chart shows a schematic view of approaches to obtain antenna factor. It's a bit messy, but also contains some problems to be investigated. The antenna factor can be obtained both by calculation and measurement. Since we are metrologists, antenna factor by the measurement are mainly focused on, and the calculation is used to validate the results. The big two methods in obtaining the antenna factor are the three-antenna method and the reference antenna method. The later one, the reference antenna method, requires standard antenna whose antenna factor is already known. Such a standard antenna should have a simple structure like a dipole to obtain its effective length theoretically. In addition, attached circuit characteristics should be predicted or measured accurately as well. In contrast, the three-antenna method doesn't have these requirements. As I mentioned in earlier slide, since antennas couple with their surrounding objects, antenna measurement, especially for antenna calibration, requires a very big space to realize a definition. These are two typical measurement environments in calibrating antennas. The left picture shows an open test site and light full-echo room. To uniquely define antenna characteristics, free space is an ideal environment to carry out the measurement. A Fourier conic room is a shielded enclosure with electromagnetic absorbing material on the inside surface. Although the construction of FAR costs very high, you can get remarkable benefits such as all weather and temperature stable environment. The absorber usually in the FAR doesn't work satisfactorily when the measurement frequency is low, and measured results often deviate from the one in free space. The other environment, open-air test site, is ordinarily constructed under the sky and has a large flat conducting plane to emulate a far free space. A remarkable advantage of the open test site is that the measured result will not be affected by the reflected signal from walls and the ceiling, even when their measurement frequency is low. To obtain an antenna parameter, such as antenna factor or gain, we must measure something that can be related to target quantity. Antenna measurements are ordinarily carried out by locating a transmitting and receiving antenna at the measurement site. By assuming each antenna has a single port, an antenna pair is basically a two-port network. A vector network analyzer is a suitable choice for such a network measurement. It provides the amplitude and the phase of each scattering parameter S11, 21, 12, and 22. Taking this into account, the antenna factor should be related to S parameters. I don't go into any more details of the S parameters, but if you were interested in the S parameter measurements, a number of textbooks has been published, and also you can find some article on the website of the vector network analyzer manufacturer. Okay, from here, let's start some groundworks. Three antenna method is a traditional method to obtain antenna factor and gain. It's a simple idea, but has a remarkable capability to implement. Although some difficulties remain in determining antenna separation, we can apply this method to many types of antennas. Here is a bit of math to manipulate. Consider the case two straight dipole antenna elements are located in free space with a field point separation of R. The transmitting antenna is excited by a source having the impedance of ZS and the voltage of V0. The open circuit voltage VOC observed at the receiving antenna port is given by this equation. LT and LR show the effective lengths of transmitting and receiving antenna respectively. Due to the time limitation, the detailed math is omitted here, but finally, a relationship between VOC and VR is obtained like the one at the bottom of this slide. By substituting VR into the definition of the antenna factor, we obtain the maximum VOC in terms of antenna factor of the receiving antenna. Next, let's consider two measurement conditions. These are equivalent circuit models of the set of antenna measurements. Figure A shows the transmitting and receiving antennas are connected to the signal source and receiver respectively. ZS and ZL are the impedances of the source and the receiver, and input impedance of the transmitting and receiving antennas is represented by ZTM and ZRM. As for figure B, it is an initial condition when their ports are directly connected by removing both antennas from the ports. Subtraction of the initial condition from the antenna measuring condition is a loss when antennas and the measurement site are inserted. The loss is ordinarily called the site insertion loss and given by this equation. After some manipulations, the site insertion loss can be expressed by using the transmitting and receiving antenna factors, FT and FR, as shown at the bottom. Term M and K containing angles can be considered as a collection term of antenna alignment. However, the small deviation of angles from the ideal antenna setting are often hard to measure. Thus, much effort should be made to align the element accurately. However, although the big effort is made to align the antenna elements accurately, we may still have a small deviation from the ideal alignment. As far as you are using dipole antenna or some other antennas having a low gain, you don't have to worry about it. Since a dipole antenna has an omnidirectional radiation pattern in the plane normal to the element axis, and a relatively broad radiation pattern in the plane containing the antenna element axis, The measurement side insertion loss is less sensitive against the deviation from the ideal element. This will be touched again in the uncertainty analysis. In the last slide, we have got the relationship between L and the antenna factors for an antenna pair. Now 3 antennas are employed and 3 different antenna pairs are made. By carrying out side insertion loss measurement for each antenna pair, we have 3 equations. After a bit boring manipulation, antenna factor of antenna 1 is obtained as shown here. The other antenna factors can be expressed in the same form. This is valid by assuming these conditions. Accordingly, the realization of definition means to satisfy these conditions. When any of them is violated, it results in the systematic error in the measurement. When a calibrated vector network analyzer is employed in the measurement, the source and the load match can be considered to have been collected to be negligibly small. For this case, loss becomes attenuation. So, the side insertion loss is called as side attenuation. In EMC measurement, side evaluation, the side attenuation have a different meaning. It is that minimum attenuation when one antenna is scanned over a specific height range above a conducting plane. Let's see some measurement examples. Take a look at the picture in the left side. 2 dipole antennas whose antenna element lengths are designed to operate around 1 GHz are in the Fourier agogic room. One antenna feed point is located right in front of the other one, and the antenna elements are aligned parallelly. One antenna was moved away from the fixed antenna on the antenna holder from 0.5 meter to 2.0 meters, and side attenuation at every 20 mm was measured. The measurements were carried out 5 times by changing dates, antenna setups, and cable connections. The vector network analyzer was recalibrated before going into each measurement. You can see 2 axes associated with a graph. Left side axis shows the average of the side attenuations, and right side axis the standard deviations. Side attenuation for each antenna pair becomes small when the increase of R and each plot is proportional to 1 over R. The measurement repeatability should have a tight relationship with the standard deviation. The standard deviation for each antenna pair is almost the same and is smaller than 0.1 dB, except for some cases throughout the scan range. By substituting these results into the equation obtained in the last slide, we can calculate antenna factors. We can carry out measurements, but how do we validate the results? Comparing the measured results with the simulated ones, that is surely ordinary way for validation. However, that approach will give you the all-over difference between two. To improve the measured result, contribution from each source of deviation should be isolated, such as the chamber characteristic and the unbalance effect caused by the real balance employed. This is one approach to implement it. To exclude the unbalance effect caused by the valence-unbalance transformer of dipole antennas, that mixed-mode antenna measurement was carried out. Thus, take SDD21 is identical to the side attenuation, although the value is almost doubled. When an ideal free space is realized, polarization of antenna element doesn't matter. Even if the antenna elements are polarized horizontally, the side attenuation should be identical to the one with the vertical polarization. An antenna scanner has been installed in a chamber. The original one is shown in the right top picture. By using this scanner, we carried out the side attenuation measurements, both with horizontal and vertical polarizations, and found that deviation becomes 0.3 dB roughly, when antenna separation becomes large. This was a curious thing for us. The chamber has been well designed, and validation has been made by the constructor. After a number of investigations, we found that the front top corner of the scanner scattered the electromagnetic fields. We added absorb blocks there and carried out the measurement again. Finally, the difference of the site attenuation between the vertical and the horizontal polarization was reduced smaller than 0.1 dB. In the last slide, we are happy with the successful improvement of the chamber characteristics. However, you have to be aware that the measured results we are looking at were at the single frequency point at 1 GHz. A careful look at the frequency response at the antenna separation, for example, R equal 1.0 meter, we can see wavy response with respect to the measurement frequency. Similar response can be found when the unexpected multiple reflection in the system happened. We investigate the measured data in 2 dimensions in frequency and separation carefully, and found that the wavy response was caused by the residual chamber reflections. We simulated the site attenuation between 2 antenna ports and used for improvement of the measured data. The measured and simulated data were transformed from frequency domain into time domain. Simulated time domain data is used as a reference to decide time gate, since this response contains no effect of the surrounding objects. Since unwanted scattered signal by the chamber should arrive sometime after the directed signal from the transmitting antenna to the receiving antenna, the amplitude and the phase of the measured SDD21 is adjusted to have the identical main response in time domain, and then time gate was applied to exclude unwanted scattered signal. By comparing the calculated and adjusted measured time domain response, we can get a suitable time gate to exclude the scattered response from the surrounding object. Then transform back to the frequency domain. A suitable time gate can be obtained by the procedure described in the last slide. So let's see what happens to the results. By applying the time gate to the time domain site attenuation, direct signal arriving at the receiving antenna can be isolated. Then, transforming it back to the frequency domain, we get the smooth frequency domain data as shown in the figure right bottom. The left figure shows the antenna factor of 3 antennas employed in the measurement with respect to the antenna separation. Since antenna factors should be independent to the antenna separation, the transmitting and receiving antenna should be sufficiently separated to avoid antenna couplings and the field non-uniformity along the antenna elements. Looking at this figure, when R becomes larger than 1 meter, antenna factor converges to a value. These are the frequency characteristics of the antenna factor for each antenna element length employed in the measurement. The dipole antenna used in this study have the replaceable antenna elements and 6 element lengths designed for 1 GHz, 1.2, 1.4, up to 2 GHz band operation are selected for the best sensitivity against the target frequency range. The left figure contains the frequency characteristic of the antenna factor for 3 antenna elements from 1 GHz to 1.4 GHz, and the right figure shows those for the remainings. Smooth plots are from the data processed antenna factor, and the associating wave plots are obtained by using the unprocessed site attenuations. The antenna factors obtained by the time gate process are pretty smooth. In contrast, these plots, antenna factors obtained by using low site attenuation oscillate centering at the time-gated ones. Finally, we'll reach the target antenna characteristics, the defined antenna factor. We went through our approach to realize the definition of antenna factor. This is just one example, and you may apply the similar way to your problem. In the previous section, we focused on obtaining target value until factor. Here, in this section, let's talk about uncertainty. Have you ever heard uncertainty? Uncertainty analysis is a math in metrology. One important thing that must be done first of all is defining the measurand. Measurand means the quantity to be measured. We defined the until factor as shown here in the last section. This is a well-known definition, but to define until factor uniquely, we should add some specific conditions. As for the E-field component must be parallel to the antenna element. E-field strength is represented by the one at the antenna feed point and given by amplitude value. Similarly, voltage need to be more specified, like the amplitude value measured across a terminal impedance of 50 ohms connected to the antenna port. Have we defined the until factor uniquely now? Not really. Antenna may be used at an open test site, maybe with horizontal polarization, maybe at a specific height such as 2.0 meters. And different measurement site may give you the different results. I should start with the term uncertainty. The international vocabulary of metrology provided terminological definitions and concepts shared among the measurement scientists. In this document, uncertainty is defined as a non-negative parameter characterizing the dispersion of quantity values being attributed to the measurand based on the information used. Do you see what it means? It's like a poem and a bit difficult to understand, to be honest. When you carry out measurement, a number of conditions can be considered, as we have seen in the last few slides. In addition, no matter whether you may be aware or not, some other conditions may affect the result. We try to realize the definition by controlling the conditions, but the controlled condition may have variations. Measurement uncertainty is a kind of combined effect from such variations. If I give you an example, in antenna measurement, the antenna separation is decided to be 3.0 meter. For example, we locate the receiving antenna at 3 meters away from the transmitting antenna by using the measuring tape. However, the separation is not always exactly 3.0000 meter. Assuming the estimated possible error in the separation is 10 millimeter, that's the assumption. The site attenuation may vary in terms of probability distribution of the separation error. This is the uncertainty associated with the antenna separation. However, many readers of that document may be confused by the additional note associated with the definition of uncertainty. It states, even if the evaluated uncertainty are small, there is no guarantee that the error in the measurement result is small. When you successfully completed your measurement campaign and luckily your uncertainty was small, don't get relief. It doesn't mean that your result is close to the defined measurand. Your result may be the best value obtained from the available information. If we are not aware of something that seriously affects measured results, our measured result may be deviated seriously from the definition. Let's see some examples. When you want to measure the source power of the signal generator, it's an extremely simple situation. You've got your power sensor, attaching it to the source port, and you can get the value, say minus 10 dBm. Does your source really output minus 10 dBm? If you got your power sensor calibrated by accredited calibration laboratory, you must apply correction factor to the measured power first. This is systematic error correction. If we don't get power sensor calculated or apply correction factor to the measured power, the systematic error remains unknown, even though the estimated uncertainty was small. This is another example of uncertainty that is sometimes omitted. A sum meter shows a room temperature 22.3 degrees Celsius. This doesn't mean that the room temperature is exactly at 22.3 degrees. Behind the digit, it is implied that the temperature is somewhere from 22.25 to 22.34 degrees Celsius. You will never know the second decimal place with this sum meter. This is an example of uncertainty caused by the lack of information. The reason why we focus on uncertainty, not error, is that the exact error of the result of the measurement is generally unknown and unknowable. All we can do is to estimate the value of input quantities and the corrections for recognized systematic effect with the standard uncertainties, actually estimated standard deviation from the samples of repeated observations, and the prior distribution based on the pool of available knowledge. This figure shows what we do in uncertainty analysis and the ideal concept behind it. Take a look at the histogram on the top left. To estimate the distribution of the measured result, we repeat observations and got result like this. From repeated observations, we got uncorrected mean and standard uncertainty that is identical to the standard deviation. When we know some systematic effects that affect the result, these effects should be corrected. And finally, we get the collected mean of observations. In collecting the observations, uncertainty of the applied correction should be combined with the standard uncertainty of the repeated uncollected observations. Now we have done our best effort to estimate the measured value and the dispersion of the quantity. Ideal concepts shown below might give you some insight of the note in a few slides back. The left bottom distribution is obtained infinite number of uncollected observations. The mean of this distribution is unknown, and also the mean may have deviation from the one in the real-world observations. Similarly, systematic effect can be collected, and then unknown distribution of possible collected observation is obtained. However, this is not be identical to the value of measurement. There still remains unknown systematic error that cause a deviation from the measurement. Remaining unknown error may include incompleteness of the definition of the measurement. Just the value of measurement, what we really want, remain unknown. Now, you understand what the note associated with the definition of uncertainty means now. I don't go into details of uncertainty analysis basics like type A and type B. You can find some textbooks elsewhere. Before we go into the measurement model is ordinarily established. I introduced a simple power measurement example before, and let's consider it. An equivalent circuit shown in the top right is a measurement model of power. The signal source power that we really want to measure is the square of A0. However, the signal source and the power sensor have their own input impedance, and this results in the mismatch error. Only when gamma L and or gamma in are 0, the displayed power is what we really want. In practice, obtaining gamma in is difficult, and much effort is made to get gamma L becomes as small as possible. Finally, the last equation is obtained, used as the mismatch model of the power measurement. Looking at the equation, gamma L and the P net affect the measured result and considered to be the source of uncertainty. As seen in the last slide, the mathematical expression of the measurement model can be expressed as a function of additional inputs. Let's assume that the measurement model can be expressed like this. W1, W2 to N are the inputs that affect Z. Note that these inputs should be independent to each other. By expanding F around the expectations of W in the first order Taylor series yield the second equation. Please be sure that deviation from the expectation mu should be small. Then taking square of each side of the equation, we will get the equation at the bottom. Here, the second term can be small enough to be ignored, and in ordinary practice, only the first term is considered. This is a common expression of the propagation of uncertainty or combined uncertainty. The partial derivatives associated with each term of input is called sensitivity coefficient. This figure shows a plot of y as a function of x. Assuming that input x has a variation around a, as shown here, that variation is linearly projected onto y. Say, the variation of x affects the variation of y, and its effect is proportional to the partial derivative of the second term of this equation. It is a nature when sensitivity coefficient is small, effects of uncertainty associated with the estimation of x become small. You may be aware this is based on the function f around the target range of x can be assumed to be linear, or range of variation of x should be sufficiently small to assume that f is linear. Let's recall the equation of three-entry method. It might have been fading out into noises. It looked like this. In the earlier slide, L123 were replaced with A123 since we consider attenuations, not losses now. Also, source and load impedance are considered to be constant. Accordingly, potential inputs that may affect the results are the frequency, antenna separation, side attenuations, and antenna alignment. Regarding antenna alignment, taking partial derivative of mismatch factors, the sensitivity coefficient for the angle will be 0. This is true when the antenna radiation and receiving patterns are not high directional. A dipole antenna relatively has a broad radiation characteristics. This need not to consider. Finally, the effect of the misalignment angles are not included in the ordinary analysis. Okay, let's start exercise. These are conditions of the uncertainty estimation. Antenna separation is assumed to have plus minus 20 mm boundary limit of uncertainty. This ordinarily means that antenna separation R surely falls into the range from 480 mm to 520 mm uniformly. In previous section, I mentioned that the antenna separation R should be longer than 1 meter to realize definition. To harmonize with that, a correction factor should be applied, but please understand this is not an example. The side attenuation measurement was repeated 10 times to obtain samples. Between measurement, antennas were rearranged, vector network analyzer was recalibrated, and the cables were reconnected to include unknown random effect as much as possible. V&M manufacturer may provide an uncertainty calculator for their products, but it is for general purpose and sometimes output unnecessarily large uncertainty. To carry out more practical uncertainty estimation, some important quantities such as dynamic range and frequency accuracy were picked up from the BNS specifications. The measured side attenuations were collected by using a calibrated stepped attenuator, and its calibration uncertainty was 0.03 dB with a coverage factor K of 2. K equal to covers 94% of data approximately. Due to the time limitation, I should omit a detailed explanation on each item. Uncertainty is orderly summarized in a table like this. This is an example of the uncertainty budget table at 2.0 GHz. Alignment angle effects are not included in this table as I explained in the slide 2 pages back. With respect to the site attenuation measurements, 3 site attenuations with different antenna pair were shown. Standard uncertainty for each pair is a combined uncertainty of the measurement reproducibility, coupling effect, linearity, dynamic range, and attenuation calibration. Except for the reproducibility of the measurement, the probability distribution is assumed to be a rectangular distribution and identical to all antenna pairs. Contribution on the far right of the table is obtained by multiplying the standard uncertainty and sensitivity coefficient. Finally, the combined uncertainty estimated by 4.9081 over meter against the calculated antenna factor of 231.81 over meter. The expanded uncertainty when the coverage factor K equal to is 0.36 in dB. The major source of final uncertainty comes from the antenna separation. In this estimation, a bit conservative antenna arrangement uncertainty like plus minus 20 mm for 500 mm antenna separation, if we could reduce it, for example plus minus 5 mm, it was significantly reduced. So far, uncertainty due to the angle is not included in the analysis, since we know the effect comes from the antenna polarization mismatch is small. However, when the variation of angle is relatively large or high-gain antennas are used in the measurement, the contribution of the angle should not be neglected. To include the effect of the angles on combined uncertainty, the higher order term of the Taylor series expansion should be considered. As a result, ignored terms shown here were taken into account. Calculating all the terms and substituting all the conditions, 3.5111 over meter should be added to the square of uncertainty by their ordinary estimation. This increased the expanded uncertainty from 0.36 dB to 0.39 dB. Since we report expanded uncertainty to the first decimal place, the angle effect can be considered negligibly small for this case. A conventional solar uncertainty analysis was performed in the last several slides. For a very complicated measurement model or nonlinear measurement model, a much powerful tool is available now. The Monte Carlo method substitutes random variables directly into the equation and obtains a distribution of the final result. The conventional procedure has 4 steps. You can replace the third step by the Monte Carlo method. All the other procedures cannot be avoided. However, obtaining sensitivity coefficients requires a big effort and the higher order term analysis necessary for nonlinear problems. Omitting this part is a great advantage. To validate the result by the traditional estimation, considering the sensitivity coefficients, the Monte Carlo method is applied to the problem. The random numbers following the probability distribution are generated for each input and substituted into the numerical model. Then you will get the distribution of the antenna factor for this problem. Standard uncertainty by the Monte Carlo method, conventional analysis with and without nonlinear analysis are 0.185 dB, 0.18 dB, and 0.19 dB respectively. Although the uncertainty obtained by the Monte Carlo method is almost identical with the one by the conventional method, the conventional method with a nonlinear term provide a result that is very close to the one by the Monte Carlo method. Now we have got measure result and uncertainty. The answer factor of our dipole antenna is just an example, but the approach we have come through can be applied to the other quantities. You may have one simple question. Actually, we need a reliable measured value to make the right decision and to put products into the market with minimum risk. But why uncertainty? To better reliability? But we now understand that even if the uncertainty was small, there is no guarantee for the small error from the true value. Slides from here and after, you may see why needed to analyze measurement uncertainty to show the reliability of your measured results. There is a concept named quality infrastructure. This is a general model of society in terms of quality. Quality means to ensure that products and services meet customers' requirements. Imagine you are in the supermarket and look for a new TV set. A number of televisions are displayed and attract you. How do you decide one? Maybe it's price, but if you find two interesting televisions in the same price range, you probably compare the specification that were provided by the manufacturer. In that case, how do you trust the value? Or how do manufacturers make their customers trust the specifications? Manufacturers produce their products by using a reliable machine and measure important quality before they put their product into the market. In addition, the test result and the procedure may be inspected by an accreditation body to add values and enhance reliability. Such an accreditation body may be investigated by another accreditation body to show their activities are strictly aligned with IEICE or something. Policymakers include the government when considering a country, decide policy, and set up rules and regulations for customers. This is the whole story how the quality infrastructure works. My organization, National Institute of Metrology of Japan, is involved here and work as one part of the QI. The quality infrastructure is generally established by the government for their country. The concept of QI becomes popular and every country has a similar social structure. It is for domestic and international as well. International trade of products and services requires equivalent standards and rules for smooth operation. In the past, although an electrical device that have passed tests in line with the international standard exported to another country, retests were forced in advance of putting the product into the local market. This is time-consuming and money-consuming as well. And finally, the local customer should pay for this cost. To realize smooth international trade, QI Institute have formed a systematic scheme to harmonize standards in the regional and international levels. QI Institute are categorized into scientific metrology, legal metrology, accreditation, and standardization. Some of you may have heard these names of the organization at the international level. Ordinarily, these international quality infrastructure organizations have regional organizations. As for the scientific metrology related to the International System Review Unit, called SI, the BIPM is an international organization and has regional metrology organizations. National Metrology Institute in Asia-Pacific region belong to Asia-Pacific Metrology Program that is one of the RMOs. BIPM maintains a database of measurement and calibration capabilities of all national metrology institutes. The database is very important to show the equivalence of the capability among the national institutes. This slide shows a simple example. When an industry exports their product to another country, In advance of shipping their products, they carry out compliance tests aligned with the target country. However, sometimes the importer in country X won't accept the test reports and request retesting in country X. The test procedure is certified by the domestic accreditation body, and the key measured values are also traceable to the national measurement standard maintained by the National Metrology Institute, AIST in Japan. Similar system should be established in country X. To show the equivalence of the test report to avoid duplicated work, it is important to show the equivalence of the traceability sources, measurement standard maintained in each country. In practice, many leaders of the National Metrology Institute have signed on the Mutual Recognition Agreement, its abbreviation MRA, that states how to realize the equivalence of the measurement standard among the institutes. The key term is traceability. When one test laboratory carried out measurements, their instrument is ordinarily calibrated by the calibration laboratory. The calibration laboratory issues calibration certificate reporting the measured value and the measurement uncertainty. Also, the calibration laboratory should have the similar system of calibration. Their standard instruments or artifacts are periodically shipped to the calibration laboratory at a higher level. Such a higher level laboratory claims a smaller uncertainty than the client. Same procedure is repeated, and at the end, the measured value and its uncertainty leads to the national standard. This hierarchy of calibration is called calibration chain. Once the equivalence of the measurement and the calibration capability of National Metrology Institute with the others was shown, the result, measured by the accredited laboratory in another country, is linked accordingly. But how to show the equivalence among the national institutes? This is the way to do it. National Metrology Institute come together and carried out international comparisons. This is a result of an international comparison. The quantity to be measured was a collection factor of an E-field probe that is defined as a ratio of the applied field strength to the indicated field strength. One E-field probe was shipped from an institute to another, and the correction factor against the E-field level of 100 volt per meter was measured at 1 GHz. KCRV is an abbreviation of the key comparison reference value, and the dotted line above and below KCRV are the deviation of standard uncertainty. Each blue dot shows the measured value provided by institute, and associating error bar shows uncertainty. Some results are not in the acceptable range compared with the KCRV and its uncertainty. This institute cannot claim their CMC to be listed on the database. Luckily, our result was acceptable. Based on this comparison results and the accreditation report on ISO 70025, we claimed our CMC to be included in the CMC database. When completed, the measured result of E-field strength in Japan can be acceptable formally in other countries. This is the whole story of measurement standard in the field of free field electromagnetic quantity measurement. In this tutorial, we went through the E-field metrology. Firstly, the definition of anti-factor to accurately measure the E-field strength and the condition required to realize the definition were considered. Then, the three entry methods to obtain anti-factor are introduced, followed by the uncertainty analysis to discuss the reliability of the measured results. Also, I touched upon the traceability of the national standard and how the National Metrology Institute claimed their calibration and measurement capability are equivalent to the other institute. Hope you can feel a flavor of metrology even a bit. Thanks for joining the session. That's all I have today. If you have any questions, I'm happy to answer.